Welcome back. It's time for our last lecture on glacial and cold climate landforms. This is one of my favorites because I just love glaciers and what they can do and how they can change the landscape. When we talk about glaciation, we have to remember that our Earth's climate fluctuates. We go through cooling periods and warming periods. The cooling periods are glacial periods where we see an extent of glacial ice both in the polar regions and in the high altitude regions. And then between, as we go through the warmer periods, we're interglacial, implying that we're going to, at some point in the future, go back to another glacial period. Now, just a quick note on climate change. This is often used as an argument as to why it's okay that we're warming because we go through warm periods and cooling periods. The warming that we've experienced the last 100 years or so has been unprecedented in how quickly it's taken place. And so, yes, we were warming a little naturally, but we shouldn't have warmed as much as we had. So that's why that argument really doesn't have the full backing of science. Now, the Pleistocene was the last period of time when we had glaciers, and it was started about 2 million years ago. And this is always strange to a lot of people that it ended quite recently. In geologic time, 10,000 years is a blink of an eye. It's very, very recent. We'd already seen humans populating most of all of the continents. We were in South America 10,000 years ago. We're starting to see some of the cities in Central Asia starting to form. So this is, in human history, relatively recent. So we populated the Earth during the last ice age. During that period of time, we had, in addition to the expanse of the ice covering the South Pole, we also had an expanse of ice over North America and Eurasia as well. Today, we've got some mountainous glaciers in the Rockies and Alps and scattered around in the Andes and different places. But for the most part, our glacial ice is held up in Antarctica and on Greenland. That's where the bulk of the ice remains today. When we talk about glaciers, there's two major types of glaciers, and these two types of glaciers overlap in a lot of the terminology, they overlap in a lot of the processes, and sometimes within a glacial area, you can have both types of glaciers existing at the same time. So we've got the continental glaciers, what you consider the large ice sheets. These are the EF climates, large areas covered with ice. Antarctica and Greenland are our only two continental glaciers we have now. The photo you see in the background is Antarctica. And when I say covered in ice, there still are mountains that poke up through the ice. And there's coastal areas that are ice-free as well, but they're covered in large part with a large sheet of ice. Now, alpine or valley glaciers, these are the ones that the ice flows through a valley. And typically, when we're referring to alpine valley glaciers, we're usually referring to those in the high altitudes, where the altitude is what gives the colder temperatures. And so as the ice forms in high valleys, it flows down a valley and it creates its own features. There is overlap. You'll have continental glaciers that have valley glaciers that flow away from the edge of the main glacier. Or as you see here again in the picture, there's an ice field in the foreground, an ice field in the background, and the ice is flowing from this higher altitude through a valley down into this lower altitude. So if the ice were to magically disappear, we'd see evidence of continental glaciation here, valley glaciation in through here, and then again back to continental glaciation in this lower ice field down here. Antarctica, the reason it has so much ice is that it's got all of your contributing factors to make it cold. It's at the highest latitude you can be, 90 degrees south. It's also a continent. So you've got, and the South Pole is pretty much near the center of the Antarctic continent. So you've got continental, it's at a high latitude, and it's also a high altitude. So the South Pole is roughly 10,000 feet in elevation. And that's an extreme environment and the perfect place to collect ice. Pretty barren. Because of the cold temperatures, there's no trees, there's no megafauna, there's no predators, land predators. There's the birds that are down here are flightless, penguins, because there's no need to flee from land predators because there are no land predators. They need to, since there's little food to be found in this area, they've got to find their food in the water. So penguins basically have adapted to fly through the water and evade water predators and hunt for food in the water as opposed to on land. Note there are no polar bears at the South Pole. There are no penguins at the North Pole. So when Christmas rolls around and that damn Coca-Cola commercial comes on where they're drinking Coke between the polar bears and the penguins, that's just wrong because we wouldn't find those two animals together at the opposite ends of the earth. Greenland, ice sheet here with mountains poking up through it. We'll talk about some of these landforms later. I got really lucky flying home from Africa on a flight, and we flew over with just perfect lighting, hitting Greenland and created nice shadows. We're running around the plane, poking ahead in any available window we could find to take pictures. The flight attendants were doing it too, and they obviously have seen this kind of stuff before, so if they were excited about it, I knew it was unusual. Now, again, with climate change, we're starting to see more melting during the summer. And so these are some of the surface ponds that appear on the surface of Greenland. Remember, water has a lower albedo than ice. And so this water is absorbing some heat, which kind of amplifies the warming and melting that's taking place on the surface of Greenland. We will talk about accumulation and ablation later, but with your continental glaciers, Greenland and Antarctica, the center of the island of Greenland, the center of Antarctica is the area where you're accumulating some snow and ice, and it flows outward under its own weight from the center of it, and then around the edges is where it melts. So with your alpine glaciers, we still have an area where we're accumulating it, and it's at the higher altitudes. Higher altitudes it collects the snow, it stays year after year, and then the weight of the ice, it flows downhill. And of course, in the mountains, downhill is going to be the valley and the valley bottom. So here's the area where we're collecting the snow, and then it flows down to the lowest point, which would be the valley bottom. Collecting higher elevation, flowing down the valley. One of my favorite things to do on vacation, if I've got an opportunity, is to go to either a volcano or a glacier. And so when we went to Chile, we got lucky because we got to see both. And so we went to the Serrano Glacier in the southern end of Chile. Look how excited I am. I'm at a glacier. It's awesome. Now, where do we get glacial ice from? Well, it's that snow that doesn't melt from year to year. So you've got to have average temperatures below 32 degrees. Which you're going to find in the interior of Greenland, which you're going to find in the interior of Antarctica, which you're going to find at the high altitudes. So you've got to have that snow stay, not melt, and accumulate. So over time, maybe in the summertime, it melts a little bit, gets softer, it gets compressed, and the weight of the next year's snow on top of it compresses it some more. It creates this kind of granular gravel-like material called firn, and then eventually that gets pushed together to become glacial ice. You hear my dog in the background? She's chasing her own tail. She's that excited about glacial ice. So this actually was in Norway, and this is firn that had fallen off one of the upper levels of a glacier that we were visiting. Here you can see like the density increasing with the weight. And so here, this crystal blue, ice is not blue in color, it's just the way light passes through it as it's been compressed together and all the air bubbles and gaps have been pushed away. So when we were at Serrano Glacier, they were chipping away at one of the little icebergs that was floating in the water. And I was all excited because the guy doing it was working the food services on our ship. So we got back to the ship, and so they served us pisco over glacial ice. And like an idiot, I took a big bite of the ice cube, forgetting that ice was formed under pressure. So it's very, very dense. It's not like ice cube ice from your freezer. This is much denser because the water molecules are compressed closer together. But it was tasty, but I almost broke a tooth. And this is what I read when I'm on vacation. The book in my lap is Over the Edge of the World, which is a book about Magellan's voyage around the world. And since I was going near the Strait of Magellan, I thought it was an appropriate book to read. And then the one I'm about to start is Collapse by Jared Diamond, how climate change has led to some civilizations over time to basically destroy their own little civilization. So it's some light vacation reading for me. I keep talking about glacial ice moving. It behaves like a fluid, a very thick, viscous fluid, moving very slow. When you talk about things moving at a glacial pace, that's the inference that glaciers aren't flying down the hill. They're slowly creeping a few inches or a few feet, depending on the glacier, every year. So when the weight of the ice pushes down on the ice enough, it causes it to deform and it causes it to push towards the lowest point. And so if you're on the side of a hill and you're pushing towards the lowest point, it's going to push it down to the valley bottom and it's going to push it downhill. If you're on a continent and you're accumulating a big pile of ice at the center of the continent, the weight of it is going to push it out to the sides, and it's going to push it out to the sides of the continent. During the summer, you may get a little bit of warming and a little bit of melt, and so there may be a thin layer of water underneath the ice in through here. But throughout the year, this top layer, since there's not a lot of weight on it, it's going to be brittle. It's going to break, because if you try and twist an ice cube, it's going to break. But if you slow, steady pressure to that ice cube over, say, a few months, you can get that ice cube to deform. But the top layer, not enough pressure on it, as the ice twists and turns as it goes down valleys, it will become brittle and break, and you'll see crevasses in the top of the ice, though the bottom part of the ice is solid. And so here you've got the weight at the center of Antarctica, the ice accumulating, and it's pushing the ice out towards the sides of the continent. If we could remove this top layer of brittle ice, underneath it would be a solid block of blue ice. Well, probably not blue because there's a lot of debris that's falling on top of it, but there'd be a solid block of ice that's moving in an S pattern down through this valley. Same thing here, solid block underneath this. It's just that top layer, as you try and bend and twist it, going around a curve, it causes it to crack and crevasses to form. Here we're going from an ice sheet at a higher elevation to an ice sheet at a lower elevation. So as the sheet moves to the top of the photo, it goes over this slight little rise, causing it to crack and create crevasses. One of the things we'll see with the photographs I've got of the glaciers, there's usually nothing for a reference for size on here. And so Antarctica especially, I'm dependent on somebody else to tell me what the size of these crevasses are. This particular one, these are about 20 to 30 feet across. A little melt on top of a glacier. So the area where the ice is accumulating, or the snow is accumulating from year over year, that's the area where the snow isn't melting. That name makes perfect sense, the zone of accumulation. And so the ice is flowing out from the zone of accumulation. It's constantly flowing downhill due to its own weight. Well, if you're moving downhill, you're moving into an area of warmer temperatures. And you're probably not going to be accumulating snow. In fact, you're going to see the opposite. You're going to see that snow melting and evaporating. Actually, ice doesn't evaporate, it sublimates, but we'll just call it evaporation for right now. So we have an area where we're losing snow. So an area where we're collecting snow, zone of accumulation, and then the area where we're losing snow, the zone of ablation. And unfortunately, ablation is not one of those terms you use in day-to-day life. And so I'm just hoping you can remember ablation is where you're losing snow. Accumulation is where you're gaining snow. And so the glacial ice flows from the zone of accumulation down into the zone of ablation. At some point, what we'll see is that the rate that the ice is coming down the hill is going to be equal to the rate at which we're losing ice at the bottom of the hill. And so we would say that it's reached equilibrium, that we're losing it as fast as we're gaining it. And then the ice will reach a constant position at the end. Even though it looks like it's not moving, the reality is that even though that edge is relatively in the same spot, that ice is still moving. It's just as this comes down the hill, we're losing it as fast as we're replacing it. Now the poor quality image you're seeing here, the snout is actually retreating just a little bit because what's happening, it's losing the ice faster than it can be replaced. And that's what we're seeing with climate change and global warming, is that we're losing the ice faster than it can be replaced. This ice is still flowing down the hill. It's just that it's melting faster than it can be replaced. And so where it was in 1978, it's backed up the hill a little bit. Okay, that was a bad expression. The ice doesn't literally back up the hill. Where the position of the end of the glacier, it changes and migrates uphill. The ice is still moving downhill. It's just melting faster than it can be replaced. And you're repeating this all around the world. Every glacial area has a net ice loss, and we're seeing over and over again places where the ice just in the past few decades has retreated miles in some cases. Antarctica especially, it's kind of been accelerated in the past 20 years in Antarctica. There's been a few models that have put initial predictions of ice loss. It's far outstripped those. Just this last February, we had the warmest temperature recorded in Antarctica at 65 degrees Fahrenheit. And so this is the beginning of February. And then just 9 days later, you'll see all of the ice in that little inlet is gone. Some of these coastal areas have retreated. There's actually some melting on top of this island here in the ice that's here. And this was just in a period of 9 days to see a pretty dramatic change in the amount of ice because of that warming. So here in 2000 to 2002, lost about a kilometer of the Columbia Glacier. We could repeat this over and over again as far as it's not just that where the end of the glacier is no longer down here, it's way up here. Its thickness has changed. So not only has it retreated, it's actually thinner back here than it was 60 years before. I've already mentioned that we're melting ahead of some of the predictions. And it's continuing about where we're losing it and how fast we're losing it. Now, this video that I'm not going to show you here because it doesn't translate well to the software I'm using for PowerPoint presentations, I'm going to put on Canvas. It's just a fascinating image to see so much ice where basically you're going to see ice that's going to heave hundreds of feet into the air. Ice blocks taller than the tallest buildings in New York collapsing and rolling through the water. It's dramatic and somewhat scary as well. But again, it's chasing ice, and it will be in the Canvas shell for this module. And having said all that about losing ice, there are some places where glacial ice is advancing, but one of which is related to climate change, and the other one is kind of its unique local situation. So the one that's related to climate change is a part of Briksdalsbreen in western Norway. And why that ice is advancing is because it's accumulating in that part of the ice sheet faster than they're losing it. And the reason it's accumulating faster is because of the warmer water in the North Atlantic, there's more evaporation. More evaporation means that there's more moisture in the air. And when that moisture, the precipitation falls in the wintertime in Norway, there's more snow in that western part of Norway, but it's because there's more moisture in the air, so then there's more snow. The Briksdalsbreen breaks off from a larger ice sheet. I believe it's called Jokstadalbreen. And Jokstadalbreen's total ice volume has been reducing. So there's just this one little finger of it that's got unusual characteristics, but it's because of more evaporation, not because of cooler temperatures. And then Hubbard Glacier in Alaska, it's a weird glacier because the bays, Disenchantment and Russell Fjord, that it goes down in are relatively shallow. And so the ice sits on the valley floor and it's kind of muddy. So every now and then it'll surge forward as it slides on the mud at the bottom of the fjord, but it's not a function of greater accumulation. It's just kind of overcoming the friction on the floor of the underneath the glacier, and it allows it to move forward in a big surge. So it's different processes. So I have relatives who deny climate change, and every now and then they'll send me articles about like either Briksdalsbreen or Hubbard Glacier, and they're sending it to all their friends saying, look, see, climate change isn't real. These glaciers are moving. So then I have to go through the science behind both of them. I do a reply all, and my relatives stopped sending me this kind of stuff, and I'm not quite sure why. I thought they'd appreciate being educated. So the physics of how the ice moves is fascinating, but what really amazes me is how glaciers can dramatically change the landscape in a very short amount of time. They can do much more damage, sorry, not damage, but changing of valleys in 1 million years than a river ever could do in that amount of time, just because of their mass and their contact with the surface is much greater than what a stream would be. And since it's a solid, not a fluid moving through an area, it has the ability to scour, scrape, and move more material than a stream could. We didn't recognize this kind of until a little bit later after some of the glacial processes have been named. So the terms like abrasion, plucking, they're so weak compared with what they should be called as like scouring, and plucking just is picking up rocks. But again, it doesn't do it justice for the amount of material that's removed by a glacier. And then we'll talk about the mass wasting as well. So what happens is the ice, as it moves over material, it's scouring the bed it's moving across. And as it scours across it, it picks up rocks, debris, sand, gravel, and that's used to grind into the surface even more, which scours more material. So it's just kind of it's a giant erosive sandpaper moving across the surface. Sometimes rock will freeze into the ice, that's plucked rocks. And then at the end, when it's melting and it's reached that equilibrium point where the ice is still flowing, the meltwater can't move that material. So we end up seeing a buildup of material as it moves out. And we'll come back to erratics later. Just remember this image of a boulder on top of the ice. So abrasion, this little striations you see on the rock, that's why they thought it was like, oh, it's just, polishing the surface. It's actually called glacial polish. And the reality is this rock was probably 100 feet thicker before the last ice age, and then it scoured it all the way back to this point. You'll see different shapes within the ice or the bedrock surface from whatever moved across it. And so you may get these weird cupping shapes. You'll get the striations and polish are more common. Then every now and then you'll get these striation rocks where they just, whatever the rock is, gets pushed so hard into the bedrock that it scours a little tunnel through the bedrock. And that's what you see here at Kelly's Island. And notice how this one has a V shape, and it's kind of conforms with the V shape here. I had a student once who was from Ohio, and they used to go play here during the summertime, and they never knew what these were for. And I was always disappointed that they didn't have signage explaining it was from the last ice age that created these unusual little tubes. Devil's Postpile behind Mammoth, the top of it is flat. And that flatness is from the glacial ice moving across it. You can see the direction that the ice moved by the striations, and that's what smoothed out the top of it. All of that grinding and pulverizing of rock as well is going to create a really fine-grained material called glacial flour. And this is a lake. The velocity of a lake is 0. We should not see sediments in it because if there's a velocity of 0, that stuff should settle to the bottom. But the slightest movement allows that glacial flour to remain in suspension. And so areas that are fed by glaciers have this characteristic blue water look to them. And it's actually, the glacial flour isn't blue. It just, the light refraction makes it look blue, but it's super fine grained material pulverized by a glacier. Now, Rocher Boutonnet, my French is horrible. As the ice moves over, you're not going to get a nice perfectly smooth surface, and what will happen is it'll abrade one side of whatever it's moving over, and then as it moves down the other side, rock will freeze into it and pluck and be pulled off the side. These can vary in size from a few feet to 50 feet high. I'll show a picture later from one in Norway that's pretty massive. When you're in a valley glacier, typically the Rocher Boutonnets are always going to point down valley, which makes perfect sense because you've got the smooth side and then the steep side. But if you're in an area that has continental glaciation where there's no valleys, how do you know which direction the ice was moving? And this one in Canada is an indicator that the ice was moving from right to left across the photograph, smoothed out one side and plucked rocks from this side. And for scale, those are somebody's legs and boots right there. The ones we saw in Finland were roughly double this length, but about the same height. And I cannot find those pictures anywhere, and it's frustrating. Here, the glacial ice as it moved across western Norway and into the North Sea removed all of the topsoil. It all froze into the glacial ice. If we look at the mountainous area before it's glaciated, your primary factor in the erosion is going to be stream erosion. And as the streams are cutting down to their base level, all of the erosion that's taking place is in the stream channel. So that's why you get this V shape to a stream cut channel in the higher altitudes. We mentioned this before when we talked about youthful streams. This stream is going to cut to its base level, which is this stream. And it's just simply a function of its gradient and the discharge is going to allow it to cut down. Notice that there's no waterfalls. We kind of see a smoothing of the interfluves. Any rough surface would be eroded away, and so you have kind of like rounded hillsides. This would be a stream-formed landscape. When the glacial ice is here, all things change. Now, instead of just having erosion in the bottom of the stream channel, that is hilarious. Now, instead of just having erosion down in where the stream channel is, we're getting erosion across the entire valley itself and the sides. And the greater the ice mass, the greater it's going to push down and remove material. And so before, these side streams feeding in were feeding down to their base level. Now the streams are cutting based on their mass. And so this smaller stream, the ice is cutting downward based on its mass. So this smaller ice flow isn't cutting down as fast as this big ice flow. And there's also, notice there's side-to-side erosion. Instead of being this V shape with a gentle slope, you've got these steeper slopes. So that side-to-side erosion is going to, as it comes in on these ridge lines, it's going to sharpen the ridge lines because the sides of these hills are being undercut from both sides. So we go from a rounded landscape to these sharp edges. And then when we remove the ice, the entire landscape has changed. So now you have these U-shaped valleys, these sharp ridges, and you have valleys where the stream isn't cutting down to its base level anymore, because what happened when this was glaciated, this ice was cutting down faster than this ice could, and it kind of leaves this U-shaped valley hanging into the side of the main valley. As far as terminology, in general, I'd be happy if you would recognize that these sharper ridge lines are indicative of glacial erosion. For terms, just this U-shaped valley, hanging valley, and horn. I'll come back to hanging valley and the U-shaped valley in just a second. But the horns would be these sharp peaks that you find in a glaciated area. And this was that smaller one that we saw on the side, showing the ice kind of eating out sideways, creating the U-shaped valley, and then retreating, leaving the U-shaped valley. The sharp edges, the arêtes, these ridge lines, the horns, and you can't see it because this is still glaciated right now. There are U-shaped valleys in through here. And of course there are horns. Wait a minute. This is a glacier carved peak, but it's in Anaheim. Well, this one's modeled after this one, the real Matterhorn in Switzerland, which is a glacier carved mountain peak. And no, for your photo project, you can't use this picture of a Matterhorn for glaciation, unless you talk about how it's related to this one. Here we've got a U-shaped valley in Yosemite Valley. And that's our third reason why Half Dome is half a dome. When I say third reason, third time we talked about Half Dome. First time because it was granite. Second time because it was an exfoliation dome. Now the third time is the half part of it, is that as the glacier cut sideways, it encountered a joint, a vertical joint in the rock, and that rock all sloughed off and it kind of amplified the vertical side of this particular valley. So you can see most of the U-shape for Yosemite Valley. There's also a hanging valley over here. The side glacier couldn't enter into the main glacier as fast. This is Bridal Veil Falls. But notice the valley floor is flat. What happened was, after the glacier retreated, this became a lake in Yosemite floor. It was called Yosemite Lake. It's not a very creative name. Or Lake Yosemite, sorry. And the velocity of a lake is 0, so it filled up with sediments and kind of flattened out the valley floor. It's roughly where El Capitan is where the end of the lake was. So as you're coming into Yosemite Valley, if you come in directly from the west, most of us come in slightly from the south. If you come in directly from the west, you can see the V shape of the canyon. About a mile, or actually 4 miles later, when you're in Yosemite Valley itself, it's this nice flat, broad area. So it's the difference between being over here versus over here in Yosemite Valley, for how dramatic the difference is in the landscape. V-shaped, not glacially carved, U-shaped from being glacially carved. Did I mention they've got a U-shaped valley with nice vertical sides? U-shape. With The melting of the glaciers after the Pleistocene, obviously sea level rises, and some of those coastal valleys that had been glaciated that have that U shape become flooded. And so a flooded coastal glacial carved valley is referred to as a fjord. It's a Norwegian term. So we have fjords in British Columbia, fjords in Alaska, fjords in Chile, and then of course what you see here is a fjord in Norway. Now, when you have the ice sheet, some of that downward pressure is amplified to the lowest point. And so these fjords can be very, very deep, deeper than you would expect, hundreds of feet deep, because the weight of all of this mass, the lowest point would have been this valley floor. And so these can be very, very deep. And then when they get into the open ocean, there's often a little bit of a lip before they get out there. So this is Grangefjorden here, and it's this area right here, which I'm going to zoom into here. And there's a little village right on the side of the hill. This dates back to the feudal period, and this is somebody's farm. That's why the trees are cleared. Now, nobody lives there now. These are just simply tourist attractions you can hike to, and I'm completely serious that when the farmer worked his fields, he was tied off so in case he tripped, he wouldn't fall into the water down below. This is a little bit higher up the side of the valley. Norway's also where you can find Preikestolen. It's the highest vertical drop. See how it kind of dips in a little bit? So in other words, if you were to jump off of here, you'd free fall longer here than you would at any other place. So if you jumped off the edge of Half Dome, it actually slopes outward ever so slightly. It's not completely vertical, so you'd bounce all the way down Half Dome. Here, you would free fall quite a long distance, neither of which I recommend. Now, these crazy Norwegians, they'll sit on the edge, they'll dangle their feet over the other side, they'll have picnic lunches up here. No, I haven't been up here yet. This is my picture from the valley floor below in a boat looking up at Preikestolen. I mentioned this before with the Hanging Valley in Yosemite Valley, the Bridal Veil Falls. That's that side glacier that's cutting in that can't cut downward as quickly as the main glacier. And so it leaves these beautiful waterfalls, and in this case, an ice fall, where this side glacier can't feed as fast as the main glacier, which is retreated way back to here. The main glacier would have been through here before, and as we've gone through this warming period, the glacial ice has retreated, leaving behind this tributary glacier feeding into it. Here's Bridal Veil Falls again, this beautiful U shape. It's a classic hanging valley. Of course, Glacier National Park, what would you expect to find there? Glaciers. So I was so excited when I saw this image because it had everything I've been talking about. It's got the hanging valley with the little diagram down here with the tributary glacier. And then the U-shaped valley, even like how they curve the U. I need to start putting that into my lecture too, where I start curving some of the words in it. And this is all of that together. There's the hanging valley. There's the U-shaped valley. Here's an arête, that sharp edge. Now, Jackson Glacier, this is the only glacier you can see from the road in Glacier National Park. It's obviously only a shadow of what it once was. The estimates that there will be no active glaciers in Glacier National Park in 2030, so in less than 10 years. I wondered if they're going to rename the glacier that used to have Glaciers National Park. So some of the this is coming in from the eastern side of the Rockies. You can see the nice, beautiful U-shaped valleys. This is multiple glaciers came into this single point and fed down valley. Clements Mountain, this is a horn. This is near Logan Pass. Wrap up tree line up into the tundra. Behind my little junior geographer here, you can see the arête in the background. And then this is actually the Continental Divide. And so here's a U-shaped valley, and that glacial ice would have fed into the Atlantic drainage system. And then this glacial ice would have fed into the Pacific drainage system. This is also where we got to see the grizzly bear. That's it down there, the grizzly bear. Whoops, went too fast. Fortunately, there was a crevasse, a little canyon between us and him because those things are really, really scary. And in part 2, we'll talk about icebergs and glacial deposition.